have the main show start today, this afternoon. We're the last three talks of the conference now. The first one will be Anna Schilling, and she's going to talk about the mystery of plethysm coefficients. Sorry.
Yeah, thank you, Frank. Yeah, thank you to the organizers for putting on this conference. I'm actually quite overwhelmed after 2 years in hiding, you know, to see all of you and to actually talk mathematics, like in coffee shops and everything. That was a great week. And well, Ben Brubaker at the beginning of the conference said he had a 2-year lead up to this conference. That's why there's so many here. So I feel already a little bit behind the curve. So the first thing I want to do before I even start, I want to announce Flipjack 2023, which will be in Davis. So I only have 1 year lead, you know. This is our logo, and we have a, we have a website already. So it's only a draft of a website, so more and more information will come. But I hope you will all solve the problems that I post this week and then present them in Davis next year. Okay, so what I want to do is talk about some hard problems, in particular the plethysm problem. And well, after Wednesday's talk, I actually introduced one extra slide just to say why should you work on a combinatorial interpretation. So this is my own motivation. So first of all, for me, it's like an inspiration to and excuse to learn more mathematics, you know. Like sometimes you see some really simple problem and it might be super hard and you try and you don't succeed, but you know, you learn other things on the way and yeah, you can learn more mathematics, even if the problem itself that you started with is hard. And you can, on the way, you can develop a better understanding of underlying structures, as Sammy said in her talk, right? There are all these structures out there that can explain certain things. So what we are going to do in this talk is we are sort of going to take a random walk and we will bump into various things on the way, like interesting mathematics. Even if Igor thinks that this problem is not solvable, we actually learn some new nice mathematics. Okay, so I want to start by just some very simple things. So what are representations? So you start with a group. So fast it will be mostly Sn, let's say, and then a vector space. And then a representation is just a homomorphism from the group to the endomorphisms of this vector space, right? And then you can define the characters, which is just a trace of this. And one thing that I want to just remind you of is that characters are actually class functions. So if you conjugate the group element, then the character doesn't change. And the reason why I'm reminding you of this is because later in the talk, we will see a generalization coming from semi-group theory, and the condition will look a little bit more complicated, okay? But really, it's sort of analogous to this. Okay, so, well, one group that we have is GLNC, right? These are n by n matrices, invertible n by n matrices. And well, how can I define this plethysm? Well, we could look at 2 GLN or GLMN and GLM representations. So one representation would go from GLN to GLM, and then you could have another one going from GLM to GLR, right? Because GLM is an endomorphism on, let's say, C to the M, right? So this these would be representations if these are homomorphisms. But you can see, if you look at it this way, you can actually compose these. Okay, so you can look at the composition of these, and then you get another GLN representation. And that's basically what plethysm is. So it's just the composition of things. And then if we look at the character of this, that's what I'm going to call plethysm. Okay, the character of this composition. Okay, so I guess most of you also know that, well, if you look at characters, there's this nice map from class functions to symmetric functions. So let's briefly look at that, because that will again come up later in the talk. So for me, Rn will be the space of class functions, and then lambda n will be the ring of symmetric functions of a fixed degree. And we have various bases for this ring of symmetric functions. So for example, they are the power sum symmetric functions. So a PR is just the sum of the monomials raised to the rth power. And then P lambda, where for me lambda now is a partition, is just the product of the parts of the partition. So that's one of the bases. And another one that we've also seen this week are the Schur functions. And well, my favorite way of defining them is as a sum over semi-standard Young tableau of a fixed shape, right? So you fix your shape lambda, and then you fill this by increasing in rows and strictly increasing in columns, and then you take these monomials x to the weight. So if you see a 1, let's say r times, you get the x to the 1 to the r and so on. Okay, so those are the Schur functions. Those are two bases. And then, so how do we get from the class functions to the symmetric functions? Well, there's this Frobenius characteristic map, which takes a class function or a character, and it maps it to the sum. So here we see the power sum symmetric function, and here's like this class function evaluated at mu. And then this z mu is just this, this number that we are all familiar with. Okay, and when we say that the Schur function is really basically an irreducible character, it's because if you take an irreducible character x lambda and you map it under this Frobenius Frobenius characteristic map, then you actually get the Schur function, and that comes from this identity on symmetric functions. So therefore, we can sort of think of characters in terms of, we can understand characters in terms of symmetric functions. Okay, so now, since I defined plethysm, well, as a composition of representations, and then I defined the character as a trace, let's see what the plethysm actually does on symmetric functions, because we also have now this map, right? So suppose I have two symmetric functions, f and g, and I know the monomial expansion of the function f. So I know that f is, let's say, x1 squared, x3 plus x2 squared, whatever. I mean, some monomial expansion. So these ai are just all the exponents that appear, right? Then the plethysm of g of x is actually, you can define it basically by saying that this is the symmetric function g evaluated at the monomials that appear in the function f, okay? Well, and plethysm in Greek just means multiplication. So I just wanted to say that. So let's do a couple of examples. Let's take S1, right? So that would be S of a single box. And so my condition was it's weakly increasing in rows, strictly increasing in columns. But if you have a single box, you basically can put any number in that single box. So the S1 in terms of monomials is just the sum of all the variables, x1 plus x2 and so on, right? So if I have some other symmetric function g, and I want to know what is g plethysm S1, well, then by my definition, I just have to plug in the monomials, but those are just the variables. So that is really just nothing else but g. So g plethysm S1 is really boring, okay? So what about, let's say, Pn? So Pn, remember, was the all the variables raised to the nth power. So if we do that, if we take some other function f, then f of Pn, then we have to do f and we evaluate it at all the powers, which is just, well, if I take my f to be, again, in terms of the monomials like this, then this would just be the ai times n. And it's easy to see that that's actually the same as Pn of f. So these are just some two simple examples to sort of get familiar with what we are doing. So what I want to do next is do another example, because this example will actually sort of show us what the combinatorics is behind this plethysm. Okay, so so please pay attention at least for this slide. So then at least you know you see some combinatorics. Okay, so what is S2? Right, S2 is two boxes, and remember we are filling it in increasing order. And now I'm going to take S2, but only in terms of two variables, x1 and x2. So that means the only numbers I can put in there are ones and twos. And I've listed the three tableaux, right, that you can write down that are weakly increasing and that only, where you only put in ones and twos. So 1, 1, 1, 2, 2, 2. And they correspond to the monomials x1 squared, x1, 2, x2 squared. Okay, so now what we want to compute is the plethysm S2 of S2. And I'm now going to do that just in terms of two variables in this slide. I mean, you could do it for more variables, but in this slide, I'm just going to take two variables. Okay, so what was our definition? Well, we take our outer S2 and we evaluate it at the monomials of the inner thing. The inner thing had three monomials, x1 squared, x1, 2, and x2 squared, right? So therefore, I'm taking S2 and I evaluate it at these three things. But now call these three things y1, y2, y3. Don't think about that they're actually x's to raised to some power. So then our definition of the Schur function says, well, take the same shape, but now we are allowed three letters because there are three variables. So I can put in the numbers 1, 2, 3. So that's what I wrote down here. 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3. So I have more terms here than up here, right? Because now I suddenly have three variables. Okay, and then, well, what monomial would I associate to 1, 1? Well, the 1 was really the x1 squared, right? I mean, that's what my 1 really stands for. So this first term is really x1 squared squared. So that's x1 to the 4th. And the 2 really stands for the x1, x2. And the 3 really stands for x2 squared. So once you plug that all in, you get this expansion. Okay, yes. Sorry, the last part was? Okay, so the question was, what are the inputs for the second S, right? So yeah, I take my inside S and I write it as in terms of a monomial expansion, which I did up here. And then the variables for the inside one, for the outside one will be the monomials. Does that answer your question? Oh, there's no, I don't care about the order because it's a symmetric function. So you can, yeah, in principle, you could put it in any order. Yeah, so okay, I chose a particular order, but yeah, you could pick a different order and you would get the same answer. Does that answer your question? Okay. Yeah, but yeah, good question. Okay, in any case, so we now know how we got this monomial expansion, but if you think about it, right? So this 1, 1, really this came from interpreting the 1. So in my ordering, I mean, you could pick a different ordering. But this 1 really corresponded to this tableau up here, 1, 1, because it corresponded to the x1 squared. So there's a better way, I guess, to, instead of writing these tableau, I'm now writing sort of tableau, right? So instead of putting the 1, I'm really putting the 1, 1, because that's what it corresponded to. And let's look, for example, at this 2, 2 term. The 2 really corresponded to 1, 2. So I put in here 1, 2, 1, 2. So I hope that you can see from this example that in general, if you wanted to compute an S lambda of S mu, or yeah, something like this, really what you would be doing is you would take the outer shape, and in what you put in are actually tableaux themselves. So these are really the objects that you get are tableau of tableau. Well, but then, yeah, so if you then write this again in terms of Schur functions, because the Schur functions are actually a basis, you get this expansion. And you can see it's positive in the Schur functions, and that's not an accident. So that's actually what this whole problem is about, that if you take a general S lambda, plethysm, a general S mu, you can write it in terms of Schur functions, but these coefficients here are all non-negative integer coefficients. And the problem is, please find a combinatorial interpretation, whatever that means. I am not going to define combinatorial interpretation. But I'm going to give you a couple for special cases, and I hope you agree that they are actually combinatorial. Yeah. Oh, yeah, yes. Oh, sorry. The question was if a variable appears with a multiplicity, then you put in yeah, yes. So you put in the monomial multiple times. Okay, so and as Sammy said in her talk, right, there's already a lot of cool structure out there with which you could try to attack something like this. And so one open problem is, well, try to find, because I just told you that the objects are just tableau of tableau, find a crystal structure on these tableau of tableau. And if you submit that to Flipjack next year, I will definitely be at your talk. Okay, so I just want to give you a couple of examples of like special cases where combinatorial sort of interpretations for the combinatorial formulas exist. And to give that to you, I need to briefly define what I mean by an even partition. So an even partition is one where all columns have even length. So here my column has length 4, and here the column has length 2. So that would be an even partition. And I call a partition a threshold partition. Well, so lambda prime is the transpose of lambda, right? So if you flip it upside down, so it's threshold if the column, the ith column, is equal to the length of the ith row plus 1. So here's an example. So this green part, basically what you do is you sort of cut at the diagonal, and then you take this green part, you transpose it, and you put it down here. So that would be a threshold partition. And it's known that if you take SH plethysm S2, you actually get the sum of Schur functions where you take the transpose of even partitions. And well, here are like 4 kind of cases where we have, I think, a nice combinatorial formula. I hope even Igor agrees. Okay, great. Yeah, so 4 nice formulas. And if you actually want to look them up, they already appeared in a paper by Littlewood, and they're also in McDonald's book on page 138. Okay. And the proof that they give to me is kind of complicated. it uses certain recurrences and so on, or generating functions. Oh yeah, here's some pictures of Littlewood and McDonald. So I wanted to give you just a sketch of how an easy proof of how you could do that. And I should say this is all work in collaboration with, I said it on my front page, but with Franco, Rosa, Mike, and Laura, who's also here. So one way of doing that is what we call the Sperp trick. So there is something called Sperp, which is basically skewing by something. So you could define the action of S lambda perp on F by this formula, where this is like the whole inner product that I think also appeared in Anton's talk. And well, if you know what S of a single row perp is on a symmetric function for all R up to sort of the degree, and if you know that that agrees on two symmetric functions, then the two symmetric functions actually have to be equal. So to show that two things are equal, you could just check whether the Sperp on them is the same. And that's actually an easy way to prove these identities that I just wrote down. Okay, and basically what you use is, well, these Sperps on the plethysms, and these are not that hard to check. Okay, so that's one way of doing it. Okay, and yeah, so one benefit of this, so even though the problem is hard, you actually get benefits out of things. Using this as Sperp trick actually gives you a very fast way of computing the plethysm. So for example, if you try to compute plethysm in Sage, it takes a very long time. Like even for like smallish examples, you wait like 4 hours until the answer spits out. But if you use this as Sperp trick, you can actually recursively compute it, and it's much faster. So that's one advantage. You think of a proof, but you actually get some practical benefit. Yeah, ask Mike to do it, to put it in actually. Oh, your question? Yeah, whether we will actually change Sage? Yes, yes, I hope so. Well, Mike or Franco, they're probably online, right? Okay. Yeah, so that's basically the part where I set up the problem. And I just very briefly want to say that there's actually also a relationship of this plethysm problem to the restriction problem. So for example, if you have a GLN representation and you want to restrict that to Sn, then, well, this will decompose into Sn representations with some multiplicities. And these coefficients you can actually also get by looking at certain plethysms. So the details don't really matter, but there are some relations between these problems. Okay, so that's, I've now set up the problem, right? So I hope you understand what the problem is. And now I'm going to start my random walk, and I'm now talking about something else, which is diagram algebras. And this I will motivate why. So this basically comes from trying to understand the representation theory behind the plethysm. And we noticed certain things, and that led us to something else, which will be in the next section, namely these uniform block permutations that we then studied. Okay, so but I first want to sort of motivate why we were interested in this uniform block permutation algebra. So we just talked about the restriction, right? So so now suppose you have some vector space where GLN acts on it, and now you take a k-fold tensor product of this, then you can restrict this action also to an Sn action, right? Just as we just did on the previous slide. So sigma, which would be an Sn, would be acting on each tensor product, on each tensor factor. And then the question is, what commutes with this action? right? So for example, if you have the GLN action, you have also the SK action, which interchanges the tensor factors. But this would be a different action because we've now restricted. And the question is, what would commute with this? And the answer was actually given by Martin and Jones. That's exactly this partition algebra, which is a diagram algebra, okay, which is called PKN. And well, the basis for this algebra, you can think of set partitions of sort of a double set, 1 up to k and 1 bar to k bar. Okay, and here's an example. So here would be, I guess k for me is equal to 8 because that's the largest letter that appears. And here would be a set partition of 1 up to 8 and 1 bar up to 8 bar. And right, so these numbers would be in a block, then the 3 is in a block by itself, and so on. So right, so I'm just partitioning the elements of the set into blocks. And you can think of this as a diagram, so that's why they call it diagram algebras. By, well, whenever something is in the same block, I sort of connect them. And the way you do connect them doesn't really matter for my purposes. It just matters that they are connected. Okay, so like here 1, 2, 4, they're in the same block, and then 2 bar, 5 bar are in the same block. So they're sort of in a connected component. Okay, and you can also multiply them, but I will just define that a little bit later when I talk about the uniform case. But basically, you can stack things on top of each other. Well, and here are pictures of Martin and Jones. Okay, so the question was like, what commutes with this SN action, right? And you can really think of this as a centralizer pair. And that's sort of what I want to talk about next, because that will motivate why you would want to think about this uniform block permutation algebra. But if I define VPN, the simple module of this algebra, then, so actually I think Georgia Bankert that we just mentioned, and Tom Halverson, and also Rosa and Mike, they have a way of giving a basis in terms of certain tableau, but I don't actually need the details. So the dimension is given by certain set value tableau. Then, so what Jones basically showed is that this k-fold tensor product will decompose into, because we have these commuting actions, into a tensor product of a PK module and an SN module. Right, so we sort of have two ways of, if you look at V to the K, we have 2 ways of looking at it. You can either have the GLN action and then the SK action, which permutes the factors, or if you restrict this GLN to SN, then the thing that commutes with it would be this partition algebra. So you have these 2 things. Okay, and then, well, now you can start learning more mathematics. So you can look at this book by Goodman and Wallach. And in there, you find that there's something about these seesaw pairs. So what are these seesaw pairs, which will now come into play? So suppose you have an algebra A, which is embedded in an algebra B. So it's a subalgebra of B, right? Then the restriction problem says, well, if you have a representation of B and you restrict it to A, it will decompose with these restriction coefficients, which I had before when we did GLN and SN. But this is now sort of in more generality. But now suppose that you have another such kind of pair. So we have now this embedding of A into B, but we also have an embedding of C into D. And suppose that B and C form a centralizer pair, and A and D form a centralizer pair. Then you learn from the book that the indices for the simple modules of B and C are actually the same. and the same for A and D, which is nice, right? So you learn something. So if we look, yeah, and you also have that then the restriction of, if you look at the module for D, the algebra D, then these coefficients are actually the same. So now let's use that, what we just learned from the book by Goodman and Wallach, and apply it to our setting, because we basically have that setting, right? We looked at V to the K, we have GLN, and in there inside we have SN. We also saw that we have this centralizer pair SN and PK, but inside PK, we also have the symmetric group, right? Because, well, we had things on the top, the unbarred letters, we had things on the bottom, and if you just put, like, connect just one element from the top to one element in the bottom, you actually get something in the symmetric group. So SK sits inside PK. And SK and GLN were also a centralizer pair. So we have exactly this seesaw, right? And therefore, we know that if you restrict from GLN to SN, well, you get these restriction coefficients, but then these coefficients also appear if you restrict the partition algebra to SK. Yes? What the action? Oh yeah, so for V, you could just take C. If you act with, let's say, GLN, you can just look at C to the N, and then you have a matrix acting on the vector. And then for the SN action, you would just permute. Oh, the other side. Yeah, okay. I'll let you know afterwards. Okay. So in any case, so we now have that this problem is sort of related to this problem. Okay, and that's what we want to do. And what we noticed was that you can actually sort of do it in two steps. So instead of starting with the PK and then restricting all the way down to SK, there's actually some algebra in between, which we call the uniform block permutation algebra. So this is now my random walk, right? We are now just doing mathematics, even though it might not have anything really to do with the original problem. But one thing that you observe is actually that if you sort of restrict from PK to UK, I haven't really defined UK yet, but I will in a second, you get something which are generalized Littlewood-Richardson coefficients, and Littlewood-Richardson coefficients we understand very well, right? And then restricting from UK to SK, that part we don't understand very well yet, but you can actually see sort of special cases of plethysm in there. So introducing this intermediate thing, you hope that you can understand something about plethysm. And that's sort of what the rest of my talk is going to be about. So now, what I have to do is I have to define what UK is. And then the goal will be to study the representation theory of this uniform block permutation algebra. And to do that, we have to learn more mathematics. So we have to learn semigroup theory, because semigroup people actually already know how to study this representation theory. So that's my random walk, right? You bump into lots of different cool mathematics. Okay, so now let me define what this algebra actually is. And so Tanabe and Kosuda actually have a slightly more general version of this, which they call the party algebra. I will comment why in a second, but I think it's a better name probably than what, yeah, the uniform block permutation algebra. But here is what the definition is for what I need. Okay, so we had these set partitions, right? So of 1 up to k, 1 bar up to k bar. But now what we want to do is we want that the number of barred letters and unbarred letters is the same in each block. So that's why we call it uniform. Okay, so that's this condition here. So the number of barred letters and unbarred letters is the same. And if you restrict to those diagrams, then that will be the subalgebra, the uniform block permutation algebra. And I think why they called it party algebra is because you sort of break, you have like a group of people, you break it into committees and you have two parties, right? And in each committee, there should be the same number of people from each party so that, you know, they can argue in the right way. I think that sort of like, I might be wrong, but this is my interpretation. Okay, so here's an example. This would be a uniform block permutation because here we have one barred letter and one unbarred letter. Here we have two. Here we have 2 and here we have 3, but always the same number of barred and unbarred letters. Okay, and you can also actually think of it now that we have the same number on top of and bottom, you can actually think of this as a size preserving bijection because the unbarred letters would be on the top and the barred letters are in the bottom, and you can think of, well, mapping the block 2 to the block 4. Because they were in the same block up here, right? So these are like size preserving bijections, and that's why we call them uniform block permutations, because they permute things, blocks of the same sizes. Okay. Yeah, and we can again view them as diagrams, right? So I can write them again in terms of diagrams. So for example, 1, 3, 1 bar, 2 bar. Here I have connected 1 and 3, and then 1 bar and 2 bar, and they are connected, and so on, right? So this would be the diagram for this particular set partition. Yeah, and before I didn't tell you how to take products, but now I can, or I will. So if you have a D, and let's say a D prime, then you can take the product by just stacking the two diagrams on top of each other and then looking at the connected components. So the connected components can become larger, right? Because you might acquire more committee members on the way when you multiply. Yeah, but I hope it's sort of clear how to do that. Okay, but you can multiply things, and we also have an identity, I should say, because if you just map 1 to 1 bar, 2 to 2 bar, and so on, that will actually act as the identity in this, yeah, if you under this multiplication. And so one thing that will become important in a moment are the idempotents of this. So let me briefly say a little bit about the idempotent. So what's an idempotent? It's just an element such that if you square it, it's equal to itself, right? So that's what an idempotent is. And you can actually characterize all the idempotents in this algebra. Namely, you basically have to, the sets at the top and the bottom, they just have to be the same. So here's an example. So instead of now looking at set partitions of the barred and unbarred letters, you only need to look at partitions of the unbarred letters. So that's what I've written here. So they are indexed by partitions of just 1 up to k. And then the partitioning in the top and the bottom is the same. So here I've connected 1 and 4, which was a block here. And then at the bottom, you also have to connect the 1 and the 4. And I hope you can see that if I stack two such things on top of each other, you get the same thing back, right? Precisely because the partitions in the top and the bottom just match up. So these are idempotents. But you can actually check that these are the only idempotents. So they form a complete set of idempotents in this uniform block permutation algebra. So I told you we can take products. We also have an identity. So this is actually a monoid, right? Because what is a monoid? You have objects, you can multiply them, you have an identity, and you have associativity. That's what a monoid is. So the structure that I explained to you is a monoid, but in fact, it's a little bit more. It's what's called a factorizable monoid. So which I'm trying to demonstrate here. So here I took an element in there, and as you can see, I now factored it. This thing on the top is an idempotent because the top and the bottom partition is the same, and the bottom is actually a permutation, right? Because they all have sort of size 1, and they just permute the dots. So I've written an element as an idempotent times a permutation, and here I've written it as a permutation times an idempotent. So that's what a factorizable monoid will do. You can take any element and you can write it as an idempotent times a permutation. So this is basically what this is saying. And remember what we set out to do. So we observed that this uniform block permutation algebra sits between the diagram algebra and SK, right? And we wanted to understand the representation theory. But now we see that this is actually a monoid, and it's a factorizable monoid. And then you look at the literature and see whether something is already known about the representation theory of monoids. Yes?
Now, did you just mean vertical permutation for a general monoid? Or do you mean permutation?
No, so the question was, do I mean invertible element, or do I mean really a permutation? No, here I really mean a permutation.
But in general, when you say factorizable monoid.
Oh, then I think this just has to be a group. Yeah. In general, yes. Yeah, I just defined it here in terms of the example at hand. Yes. Mm-hmm. In any case, so then the random walk continues. Right now we have some new structure. We want to understand it. We look at further books. And there's actually this really cool book by Ben Steinberg, which he wrote in 2016 about the representation theory of finite monoids. And it's a great book. I recommend it to everybody. And he basically develops in a readable fashion, because if you read a lot of semigroup theory, then a lot of it is not very readable. But this book is actually really readable. Oh, this will be on tape, and my collaborators might hear what I just said. So you need to take that out. Yeah, in any case, so you look at this book, and most of it is already developed. And one thing that you learn from this book is that an important thing that you need to understand inside such a monoid are the maximal subgroups. So these are sort of the largest subgroups in your monoid, if M is your monoid, that contain a certain idempotent. And why are the idempotents actually important? Because the idempotents you can sort of think as the identity in your group. So these maximal subgroups are all indexed by an idempotent, and the idempotent is, you can think of as the identity in that subgroup. Okay, so the first task at hand is then, well, let's look at the maximal subgroups in this uniform block permutation monoid. And they're actually combinatorially really easy to understand. So by top of D, I just mean the set partition in the top. And by bottom of D, I just mean the set partition at the bottom. 1 second. And then what you need for this G indexed by this E pi is that the top and bottom are the same. Yes?
Why
Yeah, so yeah, so there can be certain pieces which actually form a group. Yeah.
Can you repeat the question?
Oh, yeah, sorry. So the question was, how can you have a group inside a monoid? And yeah, you can have groups inside a monoid, like there's pieces, you know, and so basically what happens is you have your monoid and it's sort of like tiled by these pieces that actually have group structures.
One good example is maybe n by n matrices that are multiplication are a monoid. The general linear
But do you want to talk, because I don't want to repeat what you're saying. We can't hear you. Oh, why don't I give you mine?
I don't mean to usurp your talk, but n by n matrices in a multiplication form a monoid. Zero is an absorbing element, and the general linear group is a subgroup of that.
Yeah, other question?
Take the upper left.
Sorry, I can't really hear you. Can you repeat?
Okay. In n by n matrices, take matrices that are non-zero only in here. That's an item function. Again,
Yeah, sorry. Why don't you ask me afterwards? Is that okay? Sorry. It's a little bit hard to understand. But you can also ask, well, yeah, anyway, I think I'll answer after the talk. Okay, so here's an example of what I just said. So you have a set partition, right, just of the unbarred letters. I said for this maximal subgroup, right, the top and bottom, they have to be the same. So 1 and 2 both have to be separate things, and then 3 and 4 have to be connected, 5 and 6 have to be connected. And then you take all permutations within the things that have the same size. So for example, I can permute the 1 and the 2 because they have the same size. Right here, I permuted the 1 and the 2. Or because here again, I have two things of size 2. Either they go to themselves or I permute them. Right? So that's what you have. And so in general, it's actually not hard to see that these maximal subgroups are actually isomorphic to direct products of symmetric groups. So if the type of my pi is this partition, so this means it has A1 parts of size 1, A2 parts of size 2, and so on, then yeah, we are just permuting all the things of size 1, we are permuting all the things of size 2, so you can see this direct product structure. Okay, and now what would be the indexing set? So again, this you learn from reading Steinberg's book. What are the indexing sets of these simple modules? Well, you can sort of already understand because now we have these products of groups. For each symmetric group, right, the indexing set would just be a partition. And so now we just have tuples of partitions because we have these, like if you have things of size 1 or size 2, each one of those will have their own sort of partition attached to it. So we have k tuples of partitions, and well, there's just this condition that the sizes weighted by I, they have to add up to k. Okay, so here's an example. If k is equal to 3, then well, they have to add, the sizes have to, with this weighted sum, have to add up to 3. So I can have partitions of 3 in my first slot, which would be 3, 2, 1, 1, 1, 1. Or I can have a partition of 1 in my first slot and a partition of 1 in my second slot, because 1 plus 2 is equal to 3. or I can have just a partition of 1 in the third slot, because 3 times 1 adds up to 3, right? So this would be the indexing set of the modules for my uniform block permutation algebra. Okay, and then you can also develop well, nice combinatorial bases for these, and you can do that by what we called uniform tableau. So uniform tableau, again, K tuple of tableau. So they're indexed by, so they are of a given shape. So the shape is now a tuple of shapes, right? And each one of them, so SI will be of shape lambda I, the I thing in this tuple. They're all standard. So by standard, I now just mean that things don't repeat. I don't mean that things are consecutive, okay? So things just don't repeat. And then the subsets that appear are actually set partitions of K, okay? And those, yeah, the set of all those we call these uniform tableau of shape lambda. And the irreducible representations of our uniform block permutation algebra are given by the span of these tableaux. So it's, again, very analogous to what you know for like the symmetric group, where you know like standard tableau come into play. Oops. Right, so here's an example. If we take, on the last slide, right, one of the partition was 1, 1. So I would have a 1, something of size 1 in the first slot, something of size 1 in the second slot. But so the first one is like a real standard tableau, like where you have only one entry. But in the second one, you actually, you put 2 things in there. So it's sort of like a set tableau, a set value tableau. And then in the third entry, you would have things of size 3 in there and so on. Okay, so that's what you get if you study the representation theory of this. Oh yeah, and so now is where, think back to my very first slide where I said that characters, right, are class functions. So under conjugation, the character doesn't change. So for these monoids or semigroups, this is more complicated. This is the definition of when things are conjugate, okay? It looks a little complicated, and since I'm running out of time, I'm just going to leave it there. But basically, this condition, if X prime, if you were in a group and X prime was the true inverse of X, then, right, this condition would be saying that M to the W plus 1 is conjugate to N to the W plus 1. So this in a semi-group, you always have an item, a unique idempotent in the sub-monoid generated by that element. So that's what this MW is. It's in like the first page of Steinberg, so it's actually easy to understand. Okay, so in any case, we have a notion of conjugation, even though it's now more complicated than for groups, but we have that notion. And so you can now also define cycle type, like for the symmetric group, right? And so if you are in one of these maximal subgroups, since we have these products of things, you can just look at the cycle type for each of the products, and those will just be partitions. And well, if you look at the general element, which might not be sort of in one of these maximal subgroups, then what you do is you look at something that is in there, and then you define the cycle type for an element, for that element that is actually in this maximal subgroup. So that's how you define cycle type. And now I'm just going to denote by d mu the representative of a generalized conjugacy class. And yeah, so one result that we have is that if you look at the characters of the uniform block permutation algebra, you can write it as a sum of the characters of the corresponding maximal groups, right? The maximal groups were just these products of symmetric groups, so we understand that representation theory, but we actually have what these coefficients are. So that will be on the next slide. So for example, the character of U4 is the sum of these characters of the corresponding products of symmetric groups. And well, I'm just going, because I'm running out of time, I'm just going to sort of flash this at you. So we do have an expression for these coefficients, and they look very similar to, I mean, the things that appear are very similar to things that you have already seen, right? These Z lambda, but these are just products of Z lambdas. Okay, and well, so now what we want to do is we want to connect this to symmetric functions. So you can do that too. So instead of just symmetric functions in one set of variables, you can do it in multiple sets of variables. So x1, x2, and so on. So you just define analogs of power sum symmetric functions, analogs of Schur functions. So the last part will probably be a little bit quick, but What? Oh, okay, okay. Thank you. So I have 5 extra minutes. Okay. Yeah, okay, thanks. So in any case, so we have analogs of power sum symmetric functions, analogs of Schur functions. We also have like a scalar product, like the analog of the Hall inner product. Okay, and you can compute explicitly what the Frobenius characteristic of the trivial representation is. So this is the answer. Okay, so this is a product of the Schur functions, but in the different variables. And one thing that you can prove is that these coefficients that we had, right? So we had that the characters of UK is a sum of characters of these maximal subgroups. These coefficients you can actually get in terms of the symmetric functions. I mean, sort of Hall inner products of these symmetric functions. And yeah, so the character itself evaluated at one of the representatives, again, you can write in terms of these symmetric functions, which is kind of cool. These generalizations of symmetric functions, and similarly for the maximal subgroups. So even if you don't understand all the details, the upshot is you can sort of, you have an analog of what you do for the symmetric group, and you have nice combinatorics and nice tableau and so on. Okay, and here's where my random walk brings me back to the original question. So sometimes a random walk goes back to where you started. Here you can actually see that we actually have some plethysms in there, right? S lambda of S1. Okay, so that was a very boring one, but here we have S lambda 2 of S2. So that was already a more interesting one, and so on. So here we actually have a product of plethysm coefficients. And the claim is that this inner product is actually the multiplicity of VSK in this restriction. And remember, we started with PK, we went to SK, and in the middle we had the UK, right? And this restriction actually is in some way related to plethysm coefficients, even though it's not like a single one. But if you choose your lambda, your lambda vector appropriately, you could actually pick out just a single one. So we have some sort of representation theoretic understanding of, or way to get access to these coefficients. Okay, so now in my last 30 seconds, this is one other open problem that is actually related to this, which is symmetric chain decompositions of partitions in a box. So take partitions in a box, right? So here I take partitions in a box of 2 times 2. And you just look at the Young lattice, so you can just add boxes as you go, right? So this would be the Young lattice for partitions in a box of size 2 times 2. That's actually a very nice way of viewing this in terms of crystals. So you can map this directly to a crystal of a single row. And looking at these symmetric chains, so a symmetric chain would be, I put all of these, let's say these things in one chain and then this element in another chain. This is actually related to the plethysm of SW. So W is the width of my box and H is the height of my box. If I look at this in terms of 2 variables, these coefficients that you get would be precisely sort of the highest weights in the symmetric chain decomposition. And this is also an open problem, but it's related to the plethysm, the plethysm problem. So I just wanted to mention it at the very end, right? So this relates to the example we did at the very beginning. And now I'm really out of time, so thank you. But just in case you didn't learn anything, plethysm is hard, but you can still learn a lot of interesting math. And these are the collaborators on the uniform block permutation part. Thank you.
You were just calling people?
Huh?
I'll let you call on who you want.
Okay, Alex. Yeah, so
Repeat
I
the
think
question.
at least for the ones that
Repeat the question.
So, oh yeah, so Alex is asking whether I expect that there is actually a symmetric chain decomposition for crystals. And well, at least for the single row ones, I believe the answer should be yes. Yeah, I think it's a conjecture. Yeah, no, it's yes, open problem. Well, so my conjecture is for the single row crystals, but it might also be for any lambda. I mean, that I'm not sure about that one. Yeah, Brandon.
Right, I have a question about your work. Right.
I have a question about your Seesaw. Can you describe the centralizer of the party algebra?
Oh, no. Sam?
Okay.
Yeah. Jake.
My question is about the corollary at the end of section 3, where you wrote out the plethysms that you could compute. This was
Oh,
like
yeah,
2 slides back. Can you get can you pull up that slide for one moment? Actually, my question is about which simple plethysms you're getting as a special case. Like, do you get S lambda of SK? Like, is there a case where
Yeah,
you
so
just
I
have-
think you can, so if you choose your partition, this lambda vector appropriately, right? So I mean, you could choose your lambda vector to be empty, 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 a single partition something in principle. So then all of these would be just nothing, and then you would have an S lambda S single row. Yeah.
Was any case of that? I mean, I know that you showed us a few that were known before, but are those all new, or were any of those special cases previously known, or are all of those new?
So Carré Leclerc have a couple. I think they have. So they do it in terms of like ribbon tableau or domino tableau. But I think like a real combinatorial interpretation for that in general, I think is not known. Yeah, but this is not a combinatorial. I mean, I guess Igor would like hate me if I said that this was a combinatorial solution, right? This is more like a representation theoretic solution. I mean, I'm not telling you what what the numbers would be that you are counting.
So my question is about, so you have this idea of looking at something in between the symmetric group and partition algebra, the uniform, I guess, block permutation. Is it at all related to this idea, which I think Nate Harmon explained to me once?
Oh, yes, yeah.
Of instead of like studying the restriction from GLN to SN, looking at the monomial matrices or like tensoring with the torus inside, sort of in between.
Yeah, so I think Nate has done something related to this. Yeah, so I think it is really, yes, it is definitely related, yes. Sammy?
And a microphone. So David Spire and I looked at inducing like from a Young subgroup up a spect module, and it sort of lives in between this restriction that you're doing as well. So does this, because we're getting similar plethysm formulas, so are those related? Is this related to your U at all?
Okay, I think we need to talk. I don't
Okay.
know, I possibly.
Just shout.
Oh, can you shout louder, please? Oh,
Repeat the question.
the question is there, I guess you want the characterizations of partitions lambda and mu such that the expansion would just be zeros and ones, right? Yeah, not that I know of. Yeah. I mean, yeah, so there's some work also by, I guess. Yeah, I mean, there might be some partial results, but by certain people, but yeah, I'm not sure it's known in general.
Yeah, I think we should thank Anna again.